Okay, so in this experiment, one would use qualitative analysis to determine which cations, which are just positively charged species, or which anions, which are negatively charged species, are in solution. So you react them with a given solution and then observe if there is any color change, any solid formed, any smell of a gas, or any change in temperature. So I'm going to describe the process, and then you use this for your asynchronous activity or for whatever you want to use this lab for. Okay, so we use reactions that make precipitates and can lead to color change or gas evolution to identify anions or cations in solution. Anions and cations, both of them are types of ions. Okay, so you would have used wells in petri dish to do this, and you would do a table to fill up your observations. Okay, so you will initially have the solutions listed here in the wells, and then these guys would be added. These guys will be added from a dropper. So you can imagine already having sodium chloride solution, and then you add a drop of silver nitrate in there and observe, or you add a drop of sodium hydroxide, or add a drop of HCl for each run. Okay. So you can imagine adding silver nitrate in a solution of sodium chloride, or sodium hydroxide in a solution of sodium chloride, or drops of HCl in a solution of sodium chloride, and observe, or the unknown. We are not going to worry about the unknown because this is not a face-to-face lab, but the rest of the wells should be answered. Alright, so there is a table of set of rules for what salts dissolve and what do not dissolve. So typically all group 1 elements, including sodium, potassium, and ammonium polyatomic cation, are soluble. So if you have sodium sulfate, sodium nitrate, sodium carbonate, all those should be soluble. And then all nitrates are soluble, all acetates are soluble, all chlorates are soluble, perchlorates are soluble. All these polyatomic anions, when present in the salt, will make the salt soluble. All chlorides, bromides, iodide salts are soluble with an exception of lead chloride or lead bromide or lead iodide, or silver chloride, silver iodide, silver bromide, mercury iodide, bromide chloride. These are exceptions, they are not soluble. So typically, if you know the exceptions, you should know that everything else should dissolve for chlorides, iodides, and bromides. All fluorides are soluble with exception of magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, lead bromide. Those ones are not soluble. All sulfates are soluble with the exception of calcium sulfate, silver sulfate, mercury sulfate, strontium sulfate, barium sulfate, lead sulfate. Those are not soluble. Now, let's think of those guys which are mostly insoluble. Hydroxides and oxide compounds are insoluble with the exception of a few. Sodium, potassium, and barium hydroxides are soluble. Most sulfides minus 2 salts are insoluble with the exception of these few: sodium, potassium, ammonium, and barium. Most carbonates are insoluble. Most phosphates are insoluble. They don't dissolve with the exception of sodium, potassium, and ammonia. That's why point 1 was saying that his point was saying that all salts of sodium, potassium, and ammonium are soluble. That's why we're giving them as exceptions on this half part of the table. Okay, so now let's practice. This is copper nitrate. Actually, it's copper 2 nitrate, because you have copper 2 plus mixing with 2 nitrates. Okay, so it's copper 2 nitrate. Is it soluble? We have a rule for nitrates. All nitrates are soluble, so this should be soluble. Throw it in the bin. Here you have barium difluoride. Is this soluble? We go to fluorides. Rule 4. All fluorides are soluble with the exception of all these, including our barium. So barium here is not soluble. Then we have sodium sulfide. Is sodium sulfide soluble? The answer is yes. Sodium sulfide is soluble because sodium is an exception of an insoluble sulfide. It's soluble. So next, potassium oxide. Is potassium oxide soluble? Let's look for oxides. Do we have a chart on oxide? Oh, we already know that all sorts of potassium should be soluble. So potassium oxide must be soluble. We throw it into the bin. Next we have lead 2 chloride. Is lead 2 chloride soluble? We go to the rules for chlorides. All chlorides are soluble with the exception of lead, silver, mercury. So lead is an exception. It's not soluble. Insoluble bin. Is copper carbonate soluble? Most carbonates are insoluble with the exception. Here, see, most carbonates are insoluble with the exception of sodium, potassium, and ammonia, which are soluble. So copper carbonate must be insoluble. See, that's how you use this chart, and you're gonna need it for your reports, for your assignment. Okay. Solubility rules. So whenever you dissolve a salt, it might break down to ions. Those that don't break down to ions, they make what you call a precipitate. Okay. And the precipitate is an insoluble solid made during a reaction, and it stays. Okay, so you mix up ionic compounds, the ions get mixed up, you form a new product that's insoluble. We call that a precipitate. So you must be able to predict the possible products in a reaction even before you determine whether you have a precipitate or not. And to do that, we do what we call ion exchange. There's a fancy word for this term you must have learned in general chemistry. Is double displacement. This is just exchange of partner, or double replacement, depends on the book you're reading. Some people call it double decomposition, but this is wrong to say it's double decomposition because that's technically another type of reaction. So the best two terms to use is double displacement or double replacement. We are saying double because you have exchange of ions, because if you take Ki and react it with lead nitrate. What happens is there's gonna be an exchange, as you'll see in the next slide. The I goes with the lead, and then the potassium goes with the nitrate. That's why we call this double decomposition. The potassium goes with the nitrate. So remember again, there's a 1 here, so if these two goes up here, the first element is usually positively charged, you get 2 plus, and this one goes up here, that's a polyatomic anion, it's a group of elements, so the negative, the 1 will be negative up here. Okay, so that's why you see Ki written as K plus, K minus, and then you'll see lead written as lead Pb2 plus and NO3 minus. So you can imagine combining K plus and nitrate, the charges is 1-to-1 ratio. You're gonna get K potassium nitrate. All nitrates are soluble, so we give it aqueous. All nitrates are soluble, this should be aqueous. All sorts of potassium are soluble, give it aqueous. And then lead is Pb2 plus, right? When it combines with I minus, the iodide, the 2 drops down just below iodide and the 1 drops down just below lead. So you're gonna get this formula. We usually don't show the 1, so that's the formula for lead iodide, and that's it right there. Now go back to solubility rules on our table. You'll see that on rule 3, all chlorides, bromides, and iodide salts are soluble with the exception of lead, silver, mercury. So you see lead is an exception. So on here we know that lead iodide must be a precipitate. And you're going to see it in the coming slides. So immediately you mix these two together, the precipitation does not happen. These ions have to find each other. Of course, the solvent in here is H2O. Okay, the solvent is that's a nitrate pointing to. So I wanted to point at the solvent. The solvent is H2O. That's why we keep calling salts aqueous, because aqueous means a species dissolved in water. Okay, so there's gonna be breaking down of lead, nitrate, and Ki. You make your ions. So those are the 4 ions, and then those 4 ions will have to react by double decomposition or double displacement process. That's the exchange I showed you. But again, keep an eye, you have to know the charges of these guys, so that when you exchange, you know K nitrate will be like that, and then for lead iodide, you know that was Pb2 plus, and you had I minus, the 2 drops, the 1 drops, so you get that. That's the formula, and that's why you'll have to predict whether these are solid. I told you that's a solid. All nitrates are soluble, that's aqueous. Of course, all nitrates are soluble, this was aqueous. All sorts of potassium soluble, that's aqueous. Okay, so I've not told you one thing, that after you balance your ions, you should and you must do what? You must balance the species to the left and to the right. So you see, you have 2 iodides, so I have to put a 2 here to balance the I. By doing so, the K is a factor of 2, so I have to put a 2 here. That makes the nitrate 2, which is already 2 here, and it's now balanced. So the ratio is 2 to 1. There's a 1 here, and 1 to 2. So the 1 is here and the 1 is there. So you really always have to balance your equation. So this equation right here is called complete balanced equation. But we know some of these ions were spectator ions. They did not take part in the reaction. So that's why we'll have to generate ionic equation. Okay. Alright, so precipitates are solid formed during the reaction, and that's why you see there's going to be solids just down the flask. Now, what if you mix, I think in this case you are mixing what? Sodium chloride and copper nitrate. So if you do that, there's going to be an exchange, double displacement. Copper goes with, so the reaction here is sodium chloride and copper nitrate. And I think it's copper 2, so there should be a 2 here. So when those react, you get sodium nitrate, obviously because you're exchanging partners. Okay, so you get sodium nitrate. It's like swapping your boyfriend and girlfriend with another person, which is very, very immoral. That's what's happening here. So because you have copper 2, because you have copper 2 reacting with Cl minus, this 2 goes down, the 1 on Cl minus goes down. You expect the formula of copper chloride to be that. We disregard the 1 subscript, so this will be the formula, CuCl2. Okay, so those are the two products. The question is copper chloride soluble? In that case, you have to go back to the chart, look at the chlorides. All chlorides are soluble with the exception of these guys. So the chart says all chlorides are soluble with the exception of lead, silver, and mercury. Copper is not listed here. So in this case, our copper is not a precipitate, it's aqueous. So the sign that's missing here is aqueous. All nitrates are soluble. So you end up with all aqueous states. In this case, we usually say there's no reaction, because we know that when the only time we say there's a reaction is whether you're forming a gas, you're forming a solid, or you're forming a liquid in the product side. So here we'll say since all substances are soluble, they are all aqueous, there's no chemical reaction happening. There's no reaction. In fact, we don't need to show these products because all these guys will exist as ions floating in solvent. Okay. There are several types of equations. Molecular equations are complete balanced chemical equation with showing neutral compounds on every substance in reaction. So everything is neutral, no ions. Complete ionic equation, a complete balanced chemical equation showing all substances in a reaction as they actually exist in solution. They exist as charged particles, either cations or anions. Net ionic equation is when you cancel out any spectator ions and you're only showing those pieces that undergo a change. Spectator ions are those that don't play part in the reaction. They're just spectating, like you going to watch football. Now, the best way to explain what I'm trying to define here is if you write a chemical reaction like between sodium chloride and silver nitrate, you predict to get silver chloride precipitate. Okay, and sodium nitrate, all nitrates are soluble. So these are precipitate, we put S. Sodium nitrate is soluble, it's aqueous. Silver nitrate is soluble, aqueous. Sodium chloride is soluble because all sorts of sodium, potassium, and ammonia are deemed to be soluble, they are soluble. So this is the complete equation. I like calling it complete equation of reaction, and it's balanced. It's balanced. So once it's balanced, you can break down anything that's in aqueous state. Never break down anything that's in gas state. anything that's in liquid state, or anything that's solid state. You don't break those up. So sodium chloride is soluble. I'll write it as Na+, it's in group 1, this is in group 7, so I can break them like that. They're all in aqueous state. Okay, that's why it's written as Na+, Cl-. All nitrates are soluble. Silver will take a charge of plus. It's always like that. Nitrate is charge of minus. Again, it's aqueous because ionic. Silver chloride is a precipitate. You don't break it. Remember, don't break up molecules that are in gas state, liquid or solid. And then all nitrates are soluble, so we still write Na+ aqueous and nitrate. Now, to get the net ionic equation, you have to remove the spectator ions. Okay, so anything that's to the left and to the right should be taken out. Anything that's to the left and to the right should be cancelled, and then you write what's left. So you end up with the net ionic equation. This is actually only species that are reacting. The rest are just watching the game. So the overall reaction here between sodium chloride and silver nitrate only involves the chlorides and the silvers to make silver chloride precipitate. It's usually white. Okay. Now, if you want, you can write it this way. Silver and chloride, so that the formula makes sense. Okay, sometimes you get gases being formed. In fact, I will let you know that if you want to detect the presence of a carbonate, just react it with an acid, you'll always get CO2 evolved. Of course, you'll get the salt and water. So when carbonates react with acids, what you get a salt, you get CO2, and you get H2O, and then you have to balance it. So you'll see the CO2 as bubbles. So if this right there is the carbonate and you react it with, say, HCl, you're gonna see bubbles. Those bubbles is because of the presence of a carbonate with acid added in it. If you react ammonium chloride with sodium hydroxide, you're gonna get ammonia. The way to detect it is using your nose. You use wafting method, not putting your test tube directly on your nose. You just waft with your hand. There's gonna be a pungent smell of ammonia. And in fact, this is one of the reactions happening in your petri dishes. So this would have been the procedure. You just add 10 drops of the reagents to be tested, and then you add the reagents that test, and then you just record the observation. So for example, in the first row of your table, let me see if I can find it quickly. Yeah, you see, this would have been the complete chart. So we are just cutting here, looking at the first row. When you add, let's say this is a bottle having a dropper. Okay, so if you take silver nitrate and put drops on here and let it sit for a few seconds, what you're gonna see is white precipitates. So what's that white precipitate? So you're reacting these two, so sodium chloride is reacted with silver nitrate. We obviously know we need double displacement, so you get sodium nitrate. Okay, when sodium picks up the nitrate, and then the silver will pick up the chloride, so you get silver chloride. Again, silver chloride is a precipitate. Okay, so that's why we put S there, because by the table rules that's a precipitate, and that's why you see the white cloud there. So do the same. Okay, so do the same thing for the second table in your chart, in your asynchronous assignment. That's how you record silver chloride down there. So you do the same thing for sodium carbonate and silver nitrate. You should get here silver taking the carbonate. Remember, carbonate is CO2 minus, silver is Ag plus. So we'll expect that the silver will get a 2, because Ag plus and CO2 minus, CO3 2 minus will exchange their powers. Okay, so this would have been having a bracket and 1 down there, because we are dropping the 1 and dropping the 2. Okay, so that is also expected to be a white precipitate if you look at your charts. And then here you'll get silver sulfate. Here between ammonium chloride and silver nitrate, you'll get silver chloride. After the ionic equation, you get silver chloride as a precipitate, and there should be no reaction here. Of course, we are not doing unknowns. So these boxes written in red is what will be covered in the first blue. You see, we said here is silver chloride. It should be a white precipitate. This is silver carbonate. It should be a white precipitate. Silver nitrate and magnesium sulfate gives you silver sulfate. It should be a precipitate according to your table rule. Silver nitrate and ammonium chloride should give you silver chloride as a precipitate, which is white. Of course, this is just a control. It should not react with silver nitrate, and don't worry about the unknown, because this is not face-to-face lab. So I want you to predict what compounds are in these wells, but the observations are, if you react sodium hydroxide and sodium chloride, there should be no reaction, because everything is ionic in the equation of reaction. Similarly here, there's no reaction. Okay, no reaction. Let's go back, because again everything is all ionic. There's no solid in the ionic equation. But here you're gonna get magnesium hydroxide, which is sparingly soluble. It's only highly soluble when you heat the water, but in cold water does not. So you're gonna see a little bit of precipitates for magnesium hydroxide between sodium hydroxide and magnesium sulfate. Okay, so these two, when they react, that's what you'll see in the well. Now, if you take sodium hydroxide and ammonium chloride, you will not see any precipitate, but there's gonna be a gas. You will not see the gas, but it's gonna smell, and the smell is so pungent. And we already saw in an equation, okay? We already saw in the equation. Let me see if I can quickly go back. Oh my goodness. Take me back. Yeah, you see this equation? That's between ammonium chloride and sodium hydroxide. There's ammonia gas. That's the pungent smell that you would smell using by wafting. So that's what should be in this well. Okay, that's this gas. It's the ammonia gas is not green. We are just using green here so that you can know that there's a gas coming out, but it's not green. Ammonia gas is colorless and makes you cry. Okay, so don't worry about the unknown. Okay, so again, react HCl with sodium chloride. I don't expect any reaction here because all are ionic. There's no reaction. Okay, but now this is a carbonate. So react the carbonate with HCl. Here you should see bubbles. Okay, you should see bubbles. Those bubbles are because of CO2. When carbonates react with acids, they give you CO2. So a quick equation, HCl plus sodium carbonate must give you sodium chloride, the salt. It must give you CO2 and must give you H2O. So the next step is to balance it. So I see I have 2 sodiums, so let me pretend and put 2 here on the right because I have 2 on the left, and that gives me 2 chlorides, so I have to put a 2 here. There's now 2 hydrogens, there's 2 hydrogens, and then there's 2 oxygens plus 1, 3, everything is balanced. So the key point is the CO2. That's the bubbles you see right here in this well. So when carbonates reacts with acids like HCl, you get bubbles. And then for the next well, let's see, did we finish this well? Yeah, for the next well, I want you to predict what will be in there, what will be in there. Of course, here there's no reaction, and then this is just a control, and this is a control. Okay, obviously here you get magnesium chloride, which most likely is soluble, so most likely here there's no observable reaction. I'll confirm it with your charts. Alright, so that's the overview of the experiment. You should be able to answer the chart in the synchronous assignment. And I have given you all the links and resources possible under experiment 6 that should help you out.